Yes.
Perfect. Okay, so hi everyone. Thanks for the organizer for inviting me to give this talk. I really appreciate. I'm gonna discuss galactic chemical evolution, and I want to take you back to the basics. So the chemical evolution cycle and the evolution of the elements in galaxy is tightly linked to the star formation process, because when you form stars within a galaxy, you are actually creating the progenitor for all the nucleosynthesis process and astrophysical site. For example, core collapse supernovae, type 1a supernovae, low and intermediate mass star for the S process, compact binary mergers between neutron stars and black hole, other site involving binaries such as novae, rapidly accreting white dwarf, and things like that. So all of these sites are obviously going to create different elements and different isotopes. And this can become a very complicated process because all of these sites do not necessarily have the same rate. They don't occur at the same frequency. And they're going to provide their element or release them in the interstellar medium on different time scale. So we need models to be able to combine them together. And this is just one cycle. Obviously, for example, the Milky Way, there were a lot of chemical evolution cycle. The chemical enrichment process has been going on relatively continuously for the last 13 billion years. And all of this is encoded into stellar abundances. For example, here as an example from the RPA survey, Europium over iron again. This is showing the metal poor stars at low metallicity. So those are really interesting because they probe the chemical composition of the interstellar medium as it was in the early universe. And then if you look at stars that are higher in metallicity around here, you are probing stars that formed relatively recently and therefore are probing the chemical composition near the present time. So it doesn't need to be europium over iron. It's any elemental ratio that you can access with stellar spectroscopy, and you can see how this has evolved as a function of time. So it gives a very good indicator of the way element has been evolving and produced relative to each other. So now I will jump to chemical evolution models. Those are extremely useful because they allow to test the contribution of different astrophysical sites. Those are two examples. For example, to reproduce the evolution of strontium, you can ask what happened if I just add the S process from low and intermediate mass stars? What's happening if I add an R process component? What's happening if stars are rotating? If I add neutrino-driven wind, and so on. So they are really good in trying to see and unravel the different astrophysical sites that could have contributed to the evolution of a particular element. Now, of course, we should remind ourselves that all of this is very uncertain, and the reliability of chemical evolution predictions are directly affected by nucleosynthesis yields uncertainties. So we add many astrophysical sites, many sources, and we all attach nucleosynthesis yields to these processes, but they are all very uncertain, especially for the R process. And one of the main challenge for future work is to try to quantify in a robust way what is the output uncertainties of all of these predictions, and how does the nucleosynthesis uncertainties combine with galaxy evolution uncertainties, for example. Then another challenge for the future is the arrival of large data set. In the past, we were used to have plots like this for chemical evolution. For the observation, it was a couple of dots. We could just easily put them on a diagram, but now we have hundreds of thousands of stars and even millions of stars. There's a lot of large spectroscopic and photometric survey that will arrive in the future, and some of them are already there. And there's so much data that now we need to show these abundance in form of density distribution or statistical distribution. Now for models, they are also improving and increasing in complexity. And now the recent models that are 3D hydrodynamic, there's so much data that are providing for the prediction that also they have to show their prediction in forms of probability distribution functions. So we're not in the era where we combine and look at the lines through a cloud of points. Now we are in the era where we should compare predicted distribution against observed statistical distribution. Exactly how we do this in a consistent way, that's going to be quite a challenge, especially since all the survey has different selection function for their stars, for example. Another aspect I want to touch on is Gaia. Now we have kinematics of stars. So this is just one example where Bonaca, I think it's Bonaca, maybe Bonassa, I'm not exactly sure, look at some stars in the halo, which is shown here, and they plot the chemical abundances for these stars. But because of Gaia, we know how the stars are moving, so they color-coded all the abundance or the stars according to the eccentricity of the orbits of the stars. And it's really powerful. It means that not only we know the chemical composition of the stars, we now know where they are and how they move. So that provides a lot of information for theory to try to reconstruct the formation of the Milky Way. But that also brings a lot of challenge for the numerical predictions because there's now a lot of things to consider and try to reproduce simultaneously. Okay, I've been talking a lot about the evolution of the elements. Something I want to touch on is meteorites and using isotopes as also another messenger for chemical evolution and probing the origin of elements and isotopes. So in any simulation, you will evolve your chemical composition as a function of time, but at some point, you will reach the time where the solar system is forming, at least in the Milky Way. And because of meteorite, the solar system has the abundance for all the stable isotope and some radioactive one as well. And this is really unique. Meteorite provide isotopes and all the elements, which is not something that you can have by looking at stellar spectroscopy alone. So they are very complementary. Also, as we've seen yesterday by Rito's talk, there are stardust that are embedded into meteorites, and those could provide a time evolution of the isotopic ratios for a time window of about 3 billion of years prior to the formation of the solar system. So we have a lot of observation that can include isotopes in addition to using stellar spectroscopy for the element. Now, just a little example of how isotope might be useful. This is a study by Sam Jones in 2019, it's not 18, sorry about that, where we tried to provide a chemical evolution of many different isotopes. And we found that with our typical setup, we were under reproducing the neutron-rich isotope for calcium, titanium, and also chromium. And if we had a thermonuclear electron capture supernova as an extra source, we could manage to have a better match for those isotopes. And this is not something that we could have seen if we were to only look at elements. So really looking at isotope, it provides further insight into all the various astrophysical sites that could have enriched the solar system. So this is just one example. It doesn't mean that's the final solution, but isotopes can be very useful actually. Okay, I want to touch on multi-messenger astronomy and also multi-messenger chemical evolution. This is another way to reproduce, to visualize the chemical evolution cycle and the evolution of elements in galaxy. Obviously, the full picture is a lot more complicated because of all the galaxy evolution processes. But nevertheless, this cycle is encoded into stellar abundances. We also have kinematics right now. So there's also another observable, which is, as I said, the meteorites with the solar system that form at some point in the Milky Way. It's only one time shot, but at least we get a lot of isotopic information. And the thing that I really want to emphasize on this talk is that the stars that are providing the enrichment and the chemical evolution are also the same stars that provide the compact object that we see in the Milky Way and in the nearby universe. So there are neutron stars, black holes, and also white dwarfs. And those make connection between a various set of observable, for example, the gravitational wave, they are binary systems that merge together. But there's also observation regarding the mass distribution of neutron stars and black hole. This is probably an outdated picture. There's probably more reliable set of observation today. But the whole point is that all of these observable, they might look distinct and not connected together, but they are actually all connected together because the stars provide the elements and also the remnant. And chemical evolution is one of the few fields that can actually make a connection between all of these observable. And one of the big steps in the future, I think, is to have a chemical evolution simulation that manage to provide predictions for all of them. So there's nothing that prevents us from doing this right now. I think it's maybe a matter of time. And also the more constraint you add, of course, the more complicated it gets, but it also offers more opportunities. Okay, so this is my last slide, some future prospects. So the one on top is some topic that I have discussed, not in length, but still during this talk. And I wanted to provide additional points for future discussion in the working groups or for the white paper. There's also radioactive isotopes that can be included into the analysis for the early solar system, or also, as Chris Fryer mentioned, for probing the recent star formation with gamma ray telescopes. And we have an example that we have submitted on arXiv, where we are looking at the radioactive isotope ratio, and we found one that could actually be used to probe the astrophysical condition of the last R process event that polluted the solar system. So this is just an example of a diagnostic that we can add on top of stable isotope, gravitational wave signal, and elemental abundances. Also, something nice for the future is the use of age estimates instead of using iron over hydrogen. I think we're slowly getting there, but there's progress to be done. And that will really put our foot forward in the era of chemical evolution as a function of time, instead of hoping that iron is a good time tracer. And then finally, population synthesis model. Obviously, if you remember from my previous slides, the stars that produce the enrichment are the same that produce the compact objects. So having a model that is consistent, that uses the same stars for population synthesis and enrichment, all of this embedded in chemical evolution would be really a nice progress for the field. So this is not necessarily an exhaustive list. There might be something else to discuss as well, but I wanted to throw this out there as a discussion starter. All right, so I'm done. Thank you very much.
Thanks, Benoit.